Chandra, maybe you can also remind people that this is being recorded so that they know. I think you can take it from here.
Okay, thank you, Rahmat. So welcome to all attendees to our first in series of Department of Computer Science Alumni Colloquium. We just wanted to keep you aware that this talk is being recorded. So for that reason, your questions, if you can hold on till end, that would be good. So that so what you can do is put your question in the chat, and then Professor Rahmat will let you ask the question towards the end. Today's talk is by Professor Guoyu on single image depth estimation and 3D reconstruction under multi-sensing modalities. Dr. Guoyu is an assistant professor at the Chester F. Carlson Center for Imaging Science of Rochester Institute of Technology. Prior to joining RIT, he was a research scientist on autonomous driving at Ford Research and computer vision engineer at ESPN Advanced Technology Group. Dr. Liu finished his PhD and MS in computer science at the University of Delaware in our own video image modeling and synthesis lab, WIMS lab, and we are very proud of this fact. Dr. Liu obtained his master's degree in computer science at University of Toronto and master's degree in media informatics at RWTH Aachen University. He was a visiting scholar at the Auckland University of Technology. He was a research intern at Siemens Corporate Research in Princeton and Bosch Research and Technology Center in Palo Alto. He finished his bachelor degree in software engineering in Nanjing University of Post and Telecommunications with a minor in business administration and management. Dr. Liu has broad research interests spreading across computer vision, machine learning, multimedia, biomedical imaging, and robotics. He has published over 40 papers on leading international journals and conferences and 1 US patent. He is the organizer and program chair of international workshop on visual, audiometry, and computer vision applications based on location cues in conjunction with CVPR in 2017, 18, 19, and 2020. He's a guest editor of the Springer Journal of Multimedia Tools and Applications. Most importantly, he was winner of our own Frank Pearson Award in our department. He has led his team to win 2020 Incorporated LiDAR Challenge. Needless to say, I'm very proud of this moment. We were just talking about Guoyu's lab at RIT. I think he's about to graduate his own PhD student very soon. Guoyu has an inspirational journey spanning across corporate and academic worlds. I hope all aspiring students joining here ask questions and make use of this opportunity. And a quick note that we will be recording this presentation again. I'm going to share the screen where Guoyu has won this award. So here is my screen share of that. So that's the LiDAR challenge. As I understand, it's pretty recent. It's 2020. And here we see Professor Guoyu with his students picking up his third place. I think he's going for the next year or this year around, and we wish him the best. Here I present Dr. Guoyu. All yours, Guoyu.
Oh yeah, right now I can unmute. Okay, thank you very much, Chandler, for your general introduction. I'm really proud I graduated from UD and especially in WIMS lab, and finally I can come back to give a talk in our Alumni series. So I'm going to talk about some of my recent work, my lab's recent work. All the work I talk today will be this year's work in 2020. And especially I will talk about somehow the topic in the single image depth estimation and 3D reconstruction under multi-sensing modalities. Since this is Alumni talk, I will introduce a little bit myself more in addition to Dr. Chandler's introduction. Oh, I haven't shared my screen yet. Can everybody see that right now?
Yes.
Okay. Okay. So a little bit about myself, my education background is mainly into three components. First, undergraduate in China, and mainly in software engineering, and taken 2 years to learn a little bit about business organization and administration. And the second stage of my study is mainly in Europe. That is for my master's study. I studied in 2 different universities, in RWTH Aachen University in Germany, and another one in University of Trento in Italy. And that's actually a double degree program, which I don't spend quite a lot of time staying there and just earn 2 degrees. So it's quite a lot of time. People just ask me how do you earn 2 degrees there? It's not my intention to earn one master and another master. I keep earning master degrees. Not my intention. It's just happened to be that program. And finally, that comes to my final study, which is in Delaware, and I completed my master and PhD there again, and from Wim's lab. And mainly my work is on computer vision, especially in 3D registration and localization, and which I will briefly talk about later. And after graduation, I went to work, and still my working history is still mainly 3 components. Some of my work conducted when I was a student. That was mainly as an intern, research intern in different companies, and a short period as a visiting researcher in Auckland University of Technology in New Zealand. And after that, after my graduation, I went to 2 different companies. One is in ESPN, and another one is in Ford Motor Company. And after a couple of years working experience, and I joined RIT as a faculty. Right now, I'm in Carlson Center for Imaging Science, which is a department mainly working on all kinds of images, all the different stages of images as well. Okay, briefly talk about my working life after graduation. I think most students are mostly interested in what my working experience. So in ESPN is a part of Disney, and so the left image is actually a studio in ESPN. I frequently go to different studios which I have access to, and I can bring guests there. And at that time, my working station has a TV as well. And at that time, quite a lot of my colleagues just while watching different games, and they begin to while working and watching games. And at that time, I also form a habit of watching some TV and while working as well. So, and another benefit of working there is somehow I enjoy is I can go to Disney World and Disneyland for free and bring several guests together with me. And in the right hand side, this image, and probably many of you guys can recognize who she is. And actually we have Dr. Chandler just mentioned I won Frank Pearson Award. And actually Frank Pearson is this lady's younger brother. I met with her when I was in Delaware. And since I can go to Disney for free, and when I went to Disney, I met with this lady again, and there. So, but don't be misleading. I usually go to Disney not for vacation. It's mainly for working. Because I need to work there. So in the free time, in the evening, I can go to Disneyland to have some fun. Okay, and after a little bit more than half a year, I tried to get H1B, but luckily I didn't win H1B at that time. So my company just tell me either we can process your green card, but that left me half a year to process. And another one is they feel if you want to leave the company, we don't really feel bad about you. And so ESPN and Disney are not e-verified, so they cannot continue to sponsor for the extension of OPT. So eventually that leads me to the second of my job, which is in Ford Motor Company, and I work on autonomous driving. And the left side is actually myself, and with a Ford autonomous driving car with some lidars here. You can see here there are some lidar sensing result. And I was in the key autonomous driving group, and we need to give different demos to different other companies and other medias. And actually that leads to me to this image, which here, this one is me. I know this picture is not taken good, and but probably I feel this might be the only time my image is showing on New York Times and in my life. And this one at that time in 2017, this image got quite a lot of attention and put different places. But quite few people can recognize this is me, and we are giving demos to different media. Okay, and later I found out, okay, probably I want to do more research, and that leaves to me my third job, and which is actually right now my job is in RIT. So this is RIT campus. I take the picture right now, and which is from my office. And actually this is somehow from outside. This is my office. This lighting window is my office actually, and those are my students and the inside department. Okay. Now that is my working history. After that, I want to introduce the main body of this work, and which I conducted in RIT with my students. Back to the, like I mentioned, I want to briefly introduce my research when back to the time when I was in UD. When I was in Delaware, I mainly research on using images to do the registration, which is applied to a localization task. And this is one of the papers, the framework structure on which we capture videos. Actually, this is from the labs and in the Smith Hall, and we capture different rooms, buildings, rooms images, and we try to reconstruct different rooms. And whenever I want to do, I don't know where I am, I can take a video or image and to do the reconstruction. And after with the reconstruction model, and we can try to localize where I am in the building. And so we can know, okay, where am I facing at, whether I can augment some images or somehow whether I can navigate to the correct, I can be navigated to the correct place. Okay, that is back to the time when I was in UD in Vince's lab. Okay, so quite a lot of these kind of things, research is involved in 3D reconstruction. Though at that time, my research is mainly on 3D localization and registration, but absolutely reconstruction is one of the main things to be able to enable this kind of research. So that gives me more chance to do my research for my current job. And especially right now, we do quite a lot of using single images to do the 3D reconstruction and the depth estimation. So that leads to the talk today, and which there will be three main components. And the first one is shape from celluloids, 3D reconstruction. The second part is using single image to do the depth estimation in fusing with 2D LiDAR. That is what at the very beginning Dr. Campanuto has already introduced for our work in using the LiDAR to do the 3D reconstruction depth estimation. And the third one is using thermal images to do the depth estimation, which is trying to overcome the problem of night vision issues, for example, or sometimes there is a fog, and using color images, you cannot really see the depth, but using thermal, you can do that. Okay, so first, I will talk about the shape from celluloids and the 3D reconstruction. So the problem is right now, the first question is why we want to use single images. And right now we have quite a lot of videos, and why we still want to do using single image to do the reconstruction and the depth estimation. The reason it could be multiple. First, right now, 3D reconstruction, if, for example, you think about one issue, you want to reconstruct your face, and using selfie, without help from others. Is it easy that you take your mobile phone and using your mobile phone to scan around of your face? I would say most people feel that is not convenient. Instead, you want to take a selfie image, just one image you capture, and you want to do the 3D reconstruction. Okay. The second reason is quite a lot of videos, they do not really have sufficient overlap. And if you want to use a video to do the 3D reconstruction, you need to find correspondences in between the images. And with the correspondences, and you can try to use the geometry information and to do the 3D reconstruction and triangulation, those kind of things. And finally, you can do the reconstruction. But if there is no overlapping, you cannot really find correspondences. And then you cannot really do the 3D reconstruction based on just the videos. Okay. And the third reason, which is actually more practical, and from some other companies, they told me, and they need to buy images, and they need to pay for the number of images. If you buy one, that is the price. If you want to buy 2 or 10, that is another price. So if in this case, they want to reduce the cost, and in this case, using one image to do the reconstruction, that would be the best. Okay. And now we introduce why we want to use single images. And the next thing is I want to talk about is using the celluloids. What are the previous work using celluloids to do the reconstruction? And in these two, and in WCV and ECCV papers, and quite a lot of existing work are trying to do the 3D using shape from celluloids. What they try to do is trying to use the supervised learning, and they try to get a 3D reconstruction model, and with one image, and they use the 3D reconstruction model as the label, so that they can, okay, with one image, they can infer what is 3D model they look like. And that is reasonable in this kind of research, but at the same time, getting the 3D models is very expensive, like using the scanner, professional laser, or those kind of things. And first, they will use quite a lot of equipment. And the second, they will need to use extra space to do those kind of labeling, getting the scanner of the entire face, or the entire chair, or those kind of objects, 3D objects. And so that is bring quite a lot of extra costs. And the second one is there are quite a lot of papers right now trying to use some one image to get the celluloids, and from the celluloids, from one image of the celluloids, they try to do the inferring of the 3D model. But this kind of thing, this kind of research is similar to single image depth estimation, and usually they will jump in quite a lot of different holes, or those kind of discontinuities in the 3D shapes, because you cannot infer the other sides of the objects. So in summary, there are two major limitations. The first one is the current reconstruction based on single image can generate a depth map, but at the same time, they try to use just one image. They cannot do the full 3D reconstruction. The second thing is most of the current shape from celluloids work are based on supervised learning, and supervised learning are very expensive in getting the scanner and using quite a lot of time to do the labeling for the single image to do the reconstruction work. So that leads to our motivation to do the single image shape from celluloids 3D reconstruction. And first, we want to introduce a single image shape from celluloids method that can predict 3D shape just from one image without ground truth. Okay. The second thing is we want to introduce a view synthesis method to generate arbitrary number of synthesis images from different perspectives. That is following the shape from celluloids principles. And later I will talk a little bit more on what is the shape from celluloids. And the third thing is deep shape from celluloids network we propose here is to take predicted synthetic images to predict 3D models. Okay, that is the motivation of this work. And first, what is the shape from celluloids? And the shape from celluloids from the left image. And you can see actually is mainly from different cameras. And you want to see what is the objects commonly can be seen in these several objects, in these several image cameras. So with this kind of overlapping region, you can bounding the shape. You can bounding the shape of the object. Okay, so that gives us some idea. What if I can use several cameras? What about I use one image to predict quite a lot of different views, like here. if I can predict as many views as possible, I can reconstruct a 3D object as detailed as possible. So that gives us the intuition, and we want to do one image, and we interpolate those kind of images, those kind of cameras, and in different angles and different perspectives, and so that we can build a very constrained, tight constraint for the objects. Okay, that is how the intuition of this kind of work. And this is general framework for our proposed method, and mainly in two components which are connected. And the first step is trying to do the cross view prediction. For example, we will have one image as the input, and we want to predict in different other angles what they look like in other perspectives. And with other perspective, probably multiple perspectives, and we want to try to use those kind of different perspectives as kind of constraint. Okay, this side should look like in this way, and another 120 angles that should look like in this celluloid. Celluloid is a kind of mask, you can understand, and turning in another angle that should be look like in this way, so that they can be the input and the constraints for the second part, which is shaped from celluloid network and based on the cross view prediction. That is a general concept. I will introduce more details. The first part is about the cross view prediction. And the cross view prediction here is based on GAN network. And here the GAN network is trying to cross view synthesis. And we try to predict neighboring views. And here the neighboring views is 12 historical and sorry, I set up automatic transition between the slides so that I can control the time. I can know what time how much time I should spend in each slide. And what we want to do is trying to predict 12 views in this side and 30 degrees for each camera, and 12 images for horizontally, and 12 images vertically, and 12 images horizontally. So each neighboring view will be 30 degrees, and just from one image, so that we just predict so many images so that we can build geometric constraints as multiple views to overcome the ambiguity in 3D reconstruction. So here, those are the basic structure. We have one image, and we put encoding and the decoding network, and so then we predict a neighboring view. For example, here is a 30 degrees, another 30 degrees, what should it look like? And we compare with the 3D projection from the objects, and we see, okay, whether it's good enough or not. And we use the predicted view to come back and to predict what is the original image should look like, so that we can build a loss in between. And this is the general GAN idea, and the loss is relatively routine and not quite exceptional. And we mainly use the conditional GAN network, and those are the loss functions. And adversarial loss, and here is trying to use as a discriminator to distinguish the real images and the generated images, and which is here. Okay, and this is the generated image, and this is the real image, and we try to say, okay, whether they are similar or not, and then we try to use the discriminator in neural network to see, okay, whether it's real or not real. Okay, and then the second thing is we use synthesis images from the generator, and can be the input to output the simulated source images, and then we can build a loss. That is here from the cross view image. And we try to reconstruct the original image again, and try to see whether the input image and the reconstructed input are similar or not. And we build a loss function here as well. And the third one is the perception loss, and we enforce the perception similarity between the predicted and the target view. And here, that is somehow here. And these two, whether they are the same or not. Here, different from the discriminator is discriminator just decide, okay, whether it's real or not real is a binary classification thing. And but here we try to use the SSIM and some Euclidean laws to just compare with these two in celluloids. actually. Okay, those are the loss functions and the constraints, and which is mainly used for the first part, cross view synthesis. Okay, and we can predict with one image, and we can predict that many cameras and what they should look like. Okay, and the second part for this work is trying to do the 3D generator, 3D reconstruction from just one image, and we can infer the 3D shape. Okay, and here the input is just one image, and the output is a 3D object. Okay, and here with one image, and we can predict the 3D object. And from the 3D object, how can we constrain here? And we just constrain that from here, this 3D object, we try to project the 3D model into 2D views. Is something like a real object, for example, my face, and I can project my face into 30 degree, 20 degree, and 10 degree, those kind of different degrees. So each angle you can think about in camera, and you capture my 3D face in 2D in 2D view, in 2D images, and in 10 degree, 20 degree, 30 degree, you can capture my images. And those are similar idea here. We can project the 3D model into different views in 2D images. And from the 2D images, we can have the silhouettes. And from the silhouettes, from the predicted silhouettes and the regional silhouettes, we can build a constraint here, whether they are similar or not. Just we want to try to minimize the silhouettes consistency between the predicted one and the regional silhouettes one, the regional silhouettes, so that we can build this kind of constraint and to do the 3D, to train the neural network that's just using one image to infer the 3D model. Okay, and we conducted some experiments, and based on this framework, and mainly from first the visual result and giving examples and the visual synthesis and ablation study. And first, this is some of our original result, and just the left side is just one image. Okay, input. And this is actually the output of the 3D model. And we just show in two different views here. And one view and another view, here is another set of images. We have one input, and those are the 3D objects showing in different views. And we also compare with several other state-of-art methods. And this is the one image. And 5, 6, 7, 8 all published in top conferences in ECCV and CVPR, and which are the best conferences in computer vision area. And we can notice, and our result and is pretty similar, is the most similar to the ground truth. And compare with the 8, 7, those kind of things, they are missing quite a lot of details or interpreting a bad shape, but we are pretty close to the ground truth. And here, this is another view synthesis result. And we can have one image and compare with the ECCV paper in 2018. And our result is much more similar to the ground truth, and compare with 9, this paper. And is some statistic result and quantitative result. And we can see, okay, our IOU and the F score is much better than the most other state-of-art papers. Those are some other GAN networks and recently proposed. Okay, and we also conducted ablation study about how many views is better, is sufficient. For example, this is the input of the image. If you just use 6 views, and if you remember, we used 24 views initially, which are actually horizontally 12 and vertically 12. And if we just use 6, you can see there are quite a lot here. The tail of the plane is missing, and here is not very complete. And with 24 views, we can already get a much complete shape and a much more accurate shape as well. So this is an ablation study about how many views should be sufficient. Okay, actually that is another advantage. Since we have already trained a neural network to predict the neighboring views, we can predict as many as we want. And instead of just having a regional shape from silhouettes network, it is constrained by how many real cameras you have. But right now we can predict many views as possible. And just right now we show 24. Okay. So in conclusion of this work, and we propose a single image shape from celluloid network, and which we benefit from the cross-view synthesis and the 3D to 2D celluloid consistency. And instead of previous network, and we do not really use the expensive 3D labels, and which may require 3D scanners and many other sensors. Okay, and at the same time, we try to make the flexibility of generating arbitrary number of synthetic views so that we can overcome the ambiguity to reconstruct a complete and accurate shape. And we can, in this case, we can generate many images as we want, and based on the memory you have, and we can reconstruct a much more complete shape. Okay, that is the first work. And the second work is about depth estimation in fusion with 2D LiDAR, which is actually what Dr. Chandler has already introduced at the very beginning, which we won the SIG LiDAR's national challenge. And actually in that one is challenge is not really meant for just the computer science. Actually, most of the participants are from mechanical engineering, electronic engineering, and they are working on hardwares. And actually, the first and the second place, they are hardware solutions, and we are the only team that is proposing the software solution and be among the winning teams. Okay, and first, what is the problem of the current solution? And most right now in autonomous driving or some other application, they use quite a lot of high beam lidars. For example, Velodyne 64 beam, that is 80,000 in price, and that is quite expensive. And even in this case, the depth estimation is pretty sparse, and which do not have quite a lot of connections. You can see here quite a lot of connections in between the LiDAR beam. That is already 64, almost the highest one. Right now, no one use more than 64 in autonomous driving industry, and maximum they use 64. And actually, currently, most of the companies use 16 or 32. That are the major. Quite random companies use 64 beams, because with the number of beams increased, the price is increased dramatically. Okay, and even for 3D LiDAR, and we have something like 4,000 for 3D LiDAR. What is 3D LiDAR? 3D LiDAR, they have multiple beams. They can sense in the 3D environment, and that is quite expensive. And the 1632, that is something like $4,000, $8,000. And but 2D LiDAR, just one beam, and in this case, they just very expensive, not really that expensive. It's just several $100s to a couple of $1,000s. So that is much cheaper, but at the same time, it just have one beam, and you cannot really adjusting that kind of capability into the 3D scanners capability. Okay, and that is our work is trying to see, okay, how can we benefit from the LiDAR's accuracy in sensing accuracy in depth estimation, and together with cameras, which can have much higher resolution to make the 3D depth estimation and the 3D reconstruction. Okay, so in this work, our contribution is first we propose deep neural network jointly leveraging a single beam LiDAR and a camera to estimate the high precision depth. That is in combination between LiDAR and the camera. Okay, and we build a calibration system and in single beam LiDAR and digital camera, and so that we can find the correspondences between the LiDAR and LiDAR points and the image pixels. And the third one is we apply a multi-layer perception network to online estimation the correct scale, because that is the value of here. And the 2D LiDAR is usually much. 2D LiDAR is usually much more accurate, but images has higher resolution but less accurate. We want to take the advantages of both, and so this is the part of the contribution for the third point. And first, what we need to do is to do the calibration. Why? Because if you don't do the calibration, you cannot find the correspondences between the LiDAR point and the 3D point and the 3D and the images. Without this correspondence, you cannot do any correction between for the 3D reconstruction task. Okay, and that leaves us to our current work. And when we have a 2D points, we want to find correspondences. We just use something like a pen or whatever other things. We just try to say, okay, insert into this line. And we try to say, okay, let's go back to a little bit. And for example, I use my pen to somehow goes down. And whenever I see, okay, whether I have a point showing there is something like a response. If there is a high response, and that means I hit the point that has a reaction response from the LiDAR. Otherwise, I cannot really find the correspondence between the LiDAR and the 3D point. So right now I hit this point, okay, and finally as there's a response. So I can know, okay, this point and is corresponding to this pixel. And so I have a LiDAR point in corresponding. And in this case, I just need to have a line in between, and then I can find the correspondences. And most of the other current camera and to LiDAR calibration method are mainly for the 3D LiDAR together with the camera. They need to build a very expensive checkerboard, and sometimes they need to build a sphere, print a sphere. But in our current method, is really easy. We also found out the 2D LiDAR. The 2D LiDAR is traditionally very difficult for to find the correspondences, to do the calibration in between the camera and the LiDAR. But right now, from this just simple method, we can do a really good calibration between the camera and the LiDAR, and which we actually verified. And so we have those kind of correspondences. And with those correspondences, we can find 3D points and the 2D LiDAR 2D points correspondences. And with those correspondences, we can apply effective PNP, perspective endpoint algorithm, so that we can find the calibration matrix in between. And this is the transformation 3D points to the LiDAR points. And so we can actually see here, this is showing in the LiDAR 3D point, and this is we project into the images. You can find the correspondences between the 3D point and the 2D and the 3D point LiDAR point and on the corresponding pixels in the images, and this is the corresponding line. Okay, so once we have the calibration, we can use a color image to do the single image depth estimation. Here the color image is the input, and then we can try to estimate the depth. And how to estimate depth here? We use a left image and left camera and the right camera. And with the right camera, and we can actually here to try to see, okay, whether this one can recover the right image based on the appearance loss and the edge aware smoothness. Okay, so these are two losses we use, and the appearance loss is trying to say, okay, whether this image is the same as the original right image. And edge awareness is trying to estimate what is the boundary in between the depths, whether it still keep consistent with the original image boundary. Okay, so from the left image, when trained, we use left and the right two cameras. But when after training, we just use one image with the network, we can predict the depth value from here. And at the same time, since we have already do the calibration between the left camera and the 2D LiDAR, so that we can find the correspondences. Okay, in real application, we just need one. In this part, we just need to use this one image. Okay, and in online depth estimation, is too fast. In online depth estimation, and we just find these corresponding point we input into a neural network. Actually, here the neural network is not just a multi-layer perception. It's very easy one because that is mainly for online depth adjustment instead of something like offline training. And so if we have a quite complex neural network here, that will take a long time to do the adjustment. Okay. And whenever we find out, okay, this line should be the correct depth, and we try to find the corresponding depth here, depth in the image, so that when we train, okay, epoch 1, epoch 2, several epochs, and we can have a refined depth, and the refined depth is trying to say, okay, this depth estimation must fit in the corresponding pixels with this line, and then we adjust the entire image depth estimation. So we finally can dynamically adjust the depth scale based on this neural network. And this is the basic introduction of the depth estimation result. And actually, we compare with several different algorithms with just RGB images and the LiDAR input, 2D LiDAR input. We compare with 3DV and CVPR 2018 and ICCV 2019. Actually, we can see here the image is showing actually much better than the other two images. We can see, okay, this boundary is much more clear, and here these several ones compared to the depth value is less accurate than our method. Is another example. Yeah, that one is indoor, and here is outdoor environment, and compared with this several algorithms, our method is for outdoor is much more accurate. In CVPR, IROS is top robotic conference, and CVPR and ICCV top image conference, and this is the live demo. And actually, we can see here, this person is actually my student, and he is just walking, and actually this is the corresponding 2D views, 2D LiDARs, and we adjust the depth, predict depth, and to this LiDAR. And this is an outdoor environment for Kitty data set. We just extract, Kitty has quite a lot of beams, but we just extract one beam for our experiment. We predict depth and fit in this predict depth to this line so that we can find the localize, we can localize that one, and trying to get the object detected in the correct depth. And these are two online demos. Okay, and like Dr. Chandler mentioned, we have already been recognized in this competition. Actually, later I received quite a lot of emails asking us for many details about, because in the online during online announcement, they didn't really disclose as many details as possible, and this has already bring quite a lot of attention for this work, and we won the SEEK LiDAR competition for this work, and they want to show the one image, and this is one of the images. Okay. And in conclusion of this work, we propose a deep learning-based framework that explores the high performance as less costly than for the LiDARs, for the 2D LiDARs, and with our self-supervised neural network, and just using 2D LiDAR, 2D beams instead of 3D LiDAR. And we are able to conduct online learning continuously to refine the depth estimation, which enables the real-world applications instead of quite a lot of training, okay, in online adjustment. That makes the real-time application possible. And we explore the low-cost single-beam LiDAR together with single image depth estimation to obtain a high precision and depth sensing in full resolution. Here, full resolution means the image resolution. We can extend the 2D LiDAR's capability and accuracy into the 3D LiDAR's capability even in higher resolutions than normal 3D LiDAR. Okay. Okay, all of those work are mainly used for the visible world. Actually, the last one, the LiDAR one, could be used in the nighttime as well. But nighttime, since we also use the visible images, and maybe that is not that accurate in the nighttime, and that leaves us another work that is for thermal image depth estimation. Okay. And first, why we want to use thermal images, and we can see there are two examples here. And first, visible image, and in the nighttime, and you can see almost nothing. But in thermal images, you can see quite a lot of details in the images. It's not that high resolution, but still, compared with visible images, that is much better. You can see roughly the entire shape. And heavy fog. Here, the heavy fog, if you have a fog, and you cannot really see quite a lot of details in the image, but you can see quite a lot of details in the thermal images as well. Okay, so the current limitation, and for that thermal depth estimation, almost not many work actually, and just a couple actually. And existing state-of-art single image or monocular visuodometry-based single image depth estimation are mainly targeted at the visible image, which has quite a lot of textures. But for the thermal images, without many texture, that is difficult for the existing method. Okay, so that leaves us the idea of how to use thermal image to do the night vision problem, to do the single image depth estimation for thermal images, to deal with the night time, and even for autonomous driving and some other applications, navigations, and we can use these kind of techniques. And here we propose a single thermal image depth estimation neural network, which utilize visible images to help with training a thermal image. And here we also introduce an image translation network between RGB image and thermal images, which is actually, we call it a counter cyclogram. Okay, I will talk more. And finally, the success of our pipeline provides an alternative solution for active illumination LiDAR sensors for nighttime, which could be applied to autonomous driving. Okay, and the methodology, this is the main methodology, and which we use a left camera, and the color camera. Here, another right color camera together with a right thermal camera. And here, thermal camera is just one, okay? Because thermal camera is very, very expensive. And for example, if just a high resolution image with accurate sensitivity and with high sensitivity, that could be something like $10,000 to $100,000, just one camera. So that we don't really target at using two thermal cameras for training. And instead, we just try to target at more color images for training instead of using more thermal. And thermal, since we just use one for training and we just use one for the inference. Okay, and for the left image, and here we just use a thermal to color to thermal translation neural network to translate a thermal camera, left thermal camera. And at the same time, since we have been able to do left and right color image depth estimation, we can infer depth estimation from the right camera. And since the right camera and the right color camera and the right thermal camera are more or less close to each other, and we use the right color cameras image disparity. Image, you can think about disparity is kind of a depth. Okay, it's one-to-one interpolation, and the right image depth to assign to the right thermal image, which is you can think about that is kind of initialization to initialize the depth value. Okay, and once we have the left translated thermal and the right thermal image, and we can use this neural network to try to do the learning, which right image, the disparity will be used to reconstruct the left image, the left thermal image, and at the same time, left thermal image will be used to recover the right image, and we use appearance matching loss to do the learning process, to navigate the learning. Okay, this is the basic framework, and I will talk more in detail. And first of all, we need to have a translation neural network between the left image and the right image. And this is the basic pipeline for our image translation between thermal and the color camera. And we have a color camera, and we have another thermal camera, and we try to use, okay, one image, one color image, and try to do the translation for the thermal camera. And at the same time, we want to translate it back from the thermal camera to the color camera, so that we can build a consistency loss between the two color cameras. Okay, that is the basic idea. At the same time, we try to use here as to judge whether this is real or not real, and which is the discriminator. Okay, and this is the basic pipeline. In addition, we try to introduce the counter cyclograms idea, and why we want to introduce idea, and is mainly because color camera and thermal camera that are totally different. Color camera has quite a lot of textures, but thermal camera that is more smooth. but because it's reflecting the temperature. But both of the color camera and the thermal camera and their images share the consistency between the counter. For example, even if my T-shirt is somehow has quite a lot of textures, but the counter of my cell, my body, should be the same in color camera, in color images, and the thermal images. So we want to build this kind of consistency. And if here there is an edge, there is a counter, and we say, okay, if there is a counter, and then in the corresponding thermal image, there should be a counter as well. So we build this kind of consistency between color and the thermal cameras, so that we can translate it. We can build an accurate constraint between these two different modalities. If they are at the same position, if they are the same, okay, and we just don't add increasing the loss. If they are different, we just make extra operation to add the loss. Okay. So that is building the counter cycle guns consistency, and which we will use for color and thermal camera translation. And then after translation, and we will use the color camera to do the initialization for the thermal depth estimation. And here, since the initialization is done by two cameras, left camera and the right camera, we can get a depth. And after getting the depth, and we can use this depth as the initialization for the right thermal image, and which here the right thermal image is first input here, okay, and the left image it will introduce predict disparity, and here together with disparity and the left translated thermal camera from color image, and we can try to recover the right original image, and between the recovered image and the original image, we can build a constraint here. We can build a loss and try to reduce the difference, so that if that is accurate, we can have accurate depth estimation. Okay, for the right thermal camera, we have right thermal camera that for the disparity, and the left is thermal camera, and together with these two, we can reconstruct the right thermal image, and we can build a loss here. Okay, and the loss here we use two, and the first is like I mentioned here. First is the reconstructed image, and the second one is the original right thermal image. We want to make these two images reconstructed and the original one to be as similar as possible. And to make it similar, and we just use SSIM, and which is actually calculating their similarity, and if SSIM is higher, that means they are more similar. And at the same time, we try to use the intensity values to use a L1 distance in between, and try to reduce the loss, and which make it more smaller. And here, this is actually using smoothness, and which here is using the thermal images. We calculate this gradient. You can think about if the gradient is smooth, is small, and in this case, their corresponding depth should also be small, and we calculate their gradient as well. And if their gradient is large, and here the loss is also large. But at the same time, if there is a boundary in between the thermal images and between different objects, there is a significant image gradient change, and that should be big. And if here is small, and we will somehow get the loss increase, and we want to reduce this loss edge connection. Okay, and we want to show some experiment result, and first introduce some data set, because there are not many data set right now for thermal images and color images, and we will say show some thermal image translation result, and with the depth estimation, and followed by ablation study. First is the data set introduction. Actually, we have in Wim's lab, there is a CATS data set, and that is capturing LiDAR and color and thermal images. We didn't finally use it much, because it's mainly because the number of images is about 300 to 400. And when we try to train on that network, we found that it may not be sufficient. So we try to create a PT thermal kitty data set, which we use our translation network and to translate one image, the color image, into the thermal. And so the other one, so this serves as the regional thermal image, and the other image is used for online learning, and the 2 color cameras is used for online learning. And that is the thermal kitty. And another one is we captured our own data set as well. And this is the left image, right image, and the right thermal. And we capture several other things for testing. Those are the data sets we use. And this is translation neural net. This is the translation result. We have the input color image, and this is the ground truth we captured. Actually, this is RIT as well. And this is our translation. Okay, and we can see here is pretty close. And I also have a video actually here to show, which has some more results. And we show here, I can skip some slides. And this is input sequence. And this is for the depth estimation actually, and our depth estimation. But I actually want to later there will be a image translation effect. I think I can skip several. Okay, this is the translation from the input, and we translate it into our thermal image. Okay. We show that in video, but when we precise every single image. Okay, and these are some numbers, and we can see our number is much better and is higher than the other ones. And we also compare with several other methods, and this is the input image, and we translated. This is input image, and we have the depth estimation compared with other several methods, and which are in CVPR and 3DV, IROS, those kind of 3D vision and robotic conference and computer vision conferences. And we can see with a thermal input, our depth estimation result is much more accurate. One example you can see here. Here is the traffic sign, and we can see very clear boundaries and a very accurate shape of this object here. But in other several methods, they cannot really see. And here the boundary of the car is much more observable than the other several methods. Okay, those are the one sample and another sample, another set of samples with input images, and we compare with several other results. Okay, you can see here, you can see quite a lot of details in the depth estimation, but in other ones, this one is mainly wrong actually, and you cannot see the car. And so here in the road, we have a smooth transition from close to far. Okay, and those are the depth estimation results. And we also conducted ablation study. And here ablation study is trying to investigate whether the initialization with the right camera is useful or not. And so that we remove the right camera. And with the removal of the right camera, just the left image is translated into, left color image is translated into a thermal image. And with the thermal image, and we try to estimate the disparity. And with the disparity, original thermal image and the disparity, we try to recover the right image. And this pipeline should originally work in some way, but you can see without the initialization, without the right color camera initialization, the depth estimation is still a little bit worse compared with the full pipeline. You can see here is a car image, and you can vaguely see there is a car, something like a car here, but it's not as accurate as this one with the right color image initialization. The same here, and you can see here this is door, and but here that is not quite clear actually. And with the boundary here, okay, you can see here the boundaries of the car, of the door, and you can see here, but here you can not really see quite clearly. Okay. So in conclusion of this work, we propose an unsupervised single thermal depth estimation framework to enable the depth estimation. And we here introduce a counter-cycle gun idea to translate between the color image and thermal images. Okay, and that are the 3 main works. And we also applied our research in several other domains. For example, we propose to do simultaneous single image depth estimation and segmentation, which we can use the depth to help with the segmentation task, because the depth and the segmentation should be related as well. And we also try to do the depth estimation using the segmentation result as well. And I can speak a little bit. And so we compare with other scenes, even in color cameras. This is mainly for autonomous driving scenes. And with one sequence of images, we can do the depth estimation and compare with several other methods. Okay, and we also conducted our work for the plant route, and using just one image as input. Here you can see a sequence of images, but it's just to show the video. When we really do the 3D reconstruction, we are actually using just one image, and this is our result. We can replay a little bit, and to see, okay, this is the original image. We can see quite a lot of boundaries details in the route, but in other ones, and you can see here the artifacts here is not really that accurate compared with several other ones. And this is somehow using our different approaches, and this is comparable with several other methods. Okay, and we also use that for face reconstruction, for single image face reconstruction with single image face image input, and we can reconstruct different views of the images and the 3D model as well. And these are based on 2 different data sets. And with just one image in different angles, you can see quite a lot of details, textures. In normal current, most of other 3D reconstruction, face reconstruction techniques, for example, using structure from motion, or somehow the structure from motion is okay because that is using a video with quite a lot of overlapping. But for single image face reconstruction, for example, using the most commonly used is the 3D method. That is not quite a lot of details can be recovered on the face, but in here we can see quite a lot of details we can recover in the face reconstruction. Okay, and that concludes to my entire talk. And we realized both single image depth estimation and 3D reconstruction in a more robust way. Okay, and we realized single depth estimation and in multiple modalities, which we use visible images, which is the normal images captured by a mobile phone or other DSLR cameras, and we use thermal cameras, and we use thermal images, and we use LiDARs, and the different modalities we fuse together, or using one modality to help with learning with another modality. And we applied single image depth estimation and 3D reconstruction method in multiple domains and in different applications as well. Okay, and I would like to thank to my current group, and those are my groups, and with 3 PhD students right now, with 5 master students and 2 visiting scholars and PhD. And those are some fun time we went out to in Upper New York, in Upper New York State. Okay, and those are my funding support, and mainly is from RIT and Qualcomm, for the motor company, Tencent, these several big companies, and some other smaller companies, Mackinac and Circular Optics. And in the last month, I was announced that I have been awarded USDA New Investigator, and this is a standard grant which will continue for the route reconstruction work which I just showed. And with that, I want to end out my talk, and thank you for everyone. And I want to, for any questions, feel free to ask.
Great. Thank you, Guoyu, for a very nice talk. I will let Rahmat coordinate questions from.
Sure. Thank you, Guoyu, again for this great presentation. I just wanted to remind everyone that please use the participants link on the bottom of your Zoom to raise your hand, and I will unmute you to ask your question, or just kind of say something in chat to be unmuted, or kind of ask your question. So we already have 2 questions that I can read, or perhaps Patrick, if you want, I can also let you to ask your own question if you are around. Actually,
Hey,
let's
hi.
see.
Can you hear me?
Yeah, I can hear you.
Yeah, so I had a question first about great talk. Was very interested. I mainly work in state estimation, computer vision area. So I had a question about the second part of your presentation. So for your LiDAR camera calibration, when you this whole pencil logic, right? So is this finding, for example, are you trying to find the corner points of your checkerboard in the 2D LiDAR? To me, that doesn't make entire sense. I guess this 3D 2D correspondence, is that more of a like traditionally, right? You say the 2D LiDAR is a plane, right? And it would be like a plane intersection, right, to find this transformation.
Actually,
is that something that you're doing here, or
it's not really about the plane to plane. Actually, it's more about 3D to 2D. And here is using a pen. Go back. For example, in somewhere we're here, and here is a checkerboard. It's just to show an image. In reality, we don't really use checkerboard to do the calibration at all, and we just use an image. And we find out the corresponding point between the 3D point. What is the reading? Reading from, let's see, I have another. I remember there's one image. Is somewhere here. Reading from the LiDAR, we have quite a lot of correspondences. We have quite a lot of readings. It's actually XYZ 3D coordinate. And corresponding here, each pixel, we have the 2D coordinate from the image, which is X and Y. And with XYZ, a set of XYZ and a set of X and Y in 3D to 2D, we can use perspective endpoint. Here is a 6-point, actually perspective endpoint. Or in another term, that is a linear, direct linear transform. And so
yeah.
that we can
So are you like manually, because normally you use the checkerboard to do this automatically. Is this more of like a, I capture, I extract a single point from the LiDAR scan, and then I can manually annotate basically the end of the pencil in the image, right? Is that how you find the 2D correspondence in the image?
Right. Whenever I go down, actually, I just say, okay, if there is no signal in the LiDAR, and they will not have any kind of pause and this kind of response from the LiDAR. Whenever I have that, okay, I hit the point right now. I got the point. I click the point and in the image, okay, and so I can read the pixel. What is the pixel value for that? And in reality, 6 point, just 6 point, it should be enough. But in here, we just use 12, and to make it more robust.
I see. Yeah, that answers my question. Yeah, I was confused about how you were getting the 2D correspondence in the image. And then I don't know if there's. Should I ask my second question or?
Sure. Yeah, please go ahead.
Yeah. So I guess the thing. So for the last part of the presentation, basically, my question was, did you run into any trouble when dealing with the metric scale of the thermal images? For example, how did you go about performing normalization and handling different baseline temperatures? For example, if I drive around outside, each day has a different level of just average temperature, right? And this also is dependent on nighttime versus daytime. Basically, it's like it's a bias to the whole image is the way I would think about it. Basically, how is the system robust to this? How do you handle this? Was this an issue you ran into, or do you have any thoughts about it?
That's a good question. Actually, for here, we didn't really test, but we thought about that issue. That is actually that reflects in our data set as well. From indoor to outdoor, there is a contrast. in between indoor and outdoor. Even actually in outdoor capturing in the daytime and capturing the nighttime, the temperature is also different. In here, we just need to do a normalization, which takes some simple strategy, that is try to normalize the thermal images into two upper limit and a lower limit, and we stretch everything into this kind of range to do normalization to overcome this kind of what you mentioned as a bias of different season and different time. Does it answer the question, Patrick?
Yeah, Patrick was remuted, so
Sorry, I didn't realize I wasn't able to unmute. Yeah, that answers my question. Yeah, so I guess it's really dependent. You really need to collect some data in your environment, or at least.
Yeah, well, we need to do the normalization, like you mentioned. If we don't have a common something like absolute very big data set to capture everything, and the most easy thing is trying to do the normalization, and in a common range.
Yeah, it seems like an interesting problem of like what if you have a temperature sensor? Is there a correlation between like the outside temperature and these images, or something of that sort that could maybe better improve this, because your network would have normalized inputs, right? Are allows you don't have to worry about this this generalization, because it might be different. Or I mean, are you during training? I mean, I guess during training, did you add a bias to all of them? Did you try looking at that?
In training, we first normalize all the images as well. And so in testing, the same. We also need to normalize.
Okay.
Yeah.
Cool.
Like you mentioned, if we have really quite a lot of data to cover everything, maybe we don't need to do normalization. Maybe that could improve the accuracy as well. But that really requires quite a lot of effort to capturing in different seasons and across the whole year, and even in the different time. That would be quite a lot of job, quite a lot of things to do.
Got it. Thank you.
Okay. There is also one question from Lauren. I think I am unmuted, Lauren, so feel free to ask your question if you want.
Okay, so I was wondering, you showed how this kind of depth estimation can apply in daylight versus nighttime conditions. I was curious whether you could see future extensions of this work so that would be applicable in inclement weather as well, particularly for self-driving cars. Like you might be in a sunny daylight condition and then it might start to rain all of a sudden, or snow, or it might get foggy, whether you could see extending depth estimation to handle those kind of conditions as well.
Yeah, that is also a good question. Actually, that is a little bit related to just Patrick's question. I would say that it really has the data issue. So right now, not only here, but the entire community is also trying to capture different data sets to cover snow scenes or whatever other things. Actually, that we are trying to do something like using using different algorithms to do those kind of issues. I have to say, if in the training data set we don't really have snow scenes, and when you really do that in the winter with quite a lot of snow, that may have some issues here. And right now, there are two different things I would say the community is trying to do. And the one thing is they are trying to capture as more data set as possible. They are trying to cover the entire data set. And another thing is to improve some other algorithm. And some other algorithm is trying to not really totally depend on the deep neural network. And instead is a kind of combination between the original method, something like a sift feature or surf feature, those kind of features, and using some other traditional geometry-based neural network method in combination with the neural network based solution, and trying to combine with these two, because original other method, traditional method, and just use their somehow the principles and in geometry principles, especially multi-view geometry principles, to do the depth estimation, to do the reconstruction. And that could work in quite a lot of different things, but the accuracy may not be as good as training a neural network to do those kind of depth estimation and 3D reconstruction. And but if there's no training for that kind of thing, but that can deal with many more things. And right now, there's some research is trying to do in combining the original method and the neural network, trying to fit the neural network with some good result with from the traditional method, and to deal with something like unseen problem if the data is not trained in the data set in the neural network. That is another kind of research. Actually, that is something like we are trying to do as well. We try to use different kind of traditional methods in combination with deep learning, and trying to use those kind of things together to deal with something like you have never seen this kind of thing, and so that the depth estimation could still be relatively okay, maybe not perfect to really infer to be applicable, and especially in something that you have never seen. Yeah, that is something like I would tell you. And the short, long question by short is something like quite a lot of data need to be captured, and in more detail there could be some algorithm you can try to develop and try to deal with this kind of issue.
Okay, thank you.
Okay, any perhaps other question from the participants?
So I see Vineet, I have a question, but let me ask my question and then. So Guoyu, my question is, when we are translating an IR image, thermal image from visible by way of deep learning, if the ultimate goal is to detect something, then again, we go back to convolutions on that IR image, for example, to detect that. Wouldn't it be as good if we were to do similarly convolutions on that visible image to get the same object? What benefit do we get in translating a thermal image from a visible?
Translating, that is also a good question. And translating into from color to thermal here is trying to build a consistency loss in the oops, where is my mouse? Okay, and the translation between left and the right is trying to build a loss constraint here, because we want to use left and right image consistency, and so we could use here the left image and trying to do the translation and try to do recover, and so that we can simulate the stereo reconstructions principle. And if we do another way wrong, and if we say okay, we try to do using the thermal camera and trying to do the reconstruction from the translating into a color camera, or color camera is directly that may be not in our experiment. It seems like from thermal to color is less accurate than color to camera. I'm not sure whether I understand your questions exactly. Yeah.
So, for example, if our goal is to get disparity by generating the left thermal image, is it possible to get that disparity by deep learning architecture directly from a, let's say, right thermal image, or from combination of a visible and thermal image? What I'm saying is that instead of creating one other step to get what we want, and anyway the next step is by way of deep learning, why won't we get the ultimate, in this case, disparity from a deep learning architecture? Because the goal is, let's say in this case, the reconstruction. Why don't we do reconstruction directly? instead of creating, let's say, an intermediary, byproduct, if the intermediary byproduct is from some other scheme, that is one thing. But anyway, it's back to training and architectures and all that. So that's the thing. So why don't we train directly?
Yeah. Now I got you. Now I got you. Yeah. Great question. Yeah. I actually, that is something like quite a lot of work has other people's work has done in what you mentioned. Actually, the difference is we add here the intermediate step is trying to do that in an unsupervised way. And if, for example, if we have already from the thermal from here the right image or the left image, we directly get a depth value, and we try to train that. We need to have the ground truth for the depth in order to get the correct one. But right now we add a new step, and so that we can use the left and the right image to do this kind of reconstruction consistency. Actually, here actually in the training step, disparity output is the intermediate step in the training procedure. We actually want to use the thermal image and the predicted disparity to recover the right one. And here the recover the right one, maybe in the first iteration, the left translated thermal and the original right thermal image here is not accurate. So the recovery here is also not good. I should, and here, this is more clear. Here the right thermal, here if the thermal disparity is not good, and so the left translated image, and here they cannot really recover the right thermal images very well. And so maybe after several iterations, and we can recover very well. That means the disparity is accurate. And if we use direct method to interpolate from, okay, let's say the right image into a disparity, that is also possible. And actually quite a lot of work has been, previous work is doing in that way. But that really requires the ground truth steps. And here we just trying to avoid supervision from the depth size, from the direct depth estimation. And instead, we want to build a unsupervised way to try to navigate this process.
Got it. Thank you.
Yeah. Okay, so perhaps maybe I can also read the last question from Vinit, and I would assume that if there are additional questions, perhaps people also can reach out to Guoyu later as well. I'm sure that he will be available. So the question, I think you can also read it in the chat. So
I can speak it myself too.
Oh yeah, okay. So I thought that you are still muted. So yeah, please go ahead.
Hello, Dr. Lalu. I had a question regarding the 2D to 3D generator in the shape from silhouettes. So my question is that since deep learning requires the tensor in the batches to be of the same dimensions, I'm assuming that the reconstructed mesh would be having the same number of triangles or same number of edges or same number of vertices, one of those. So does that affect the accuracy of the reconstructed mesh?
Here you are talking. I was sliding the PPT.
Okay, I can repeat my question.
Yeah.
Sure. So in the 3D generator, in the shape from silhouette module, so since deep learning requires the tensors to be in a batch to be of the same size, I'm assuming the number of triangles or vertices or the edges in the reconstructed mesh should be the same. So, but
right, that is the same. That is the same size. It's actually 250 by 250 in that space.
Oh, 250.
Yeah, the output is fixed. The output size is fixed.
Okay, so 250 number of faces.
Oh, not faces, the output dimension. I mean, the output, the 3D object dimension. I mean.
Oh, okay. So it's just an embedding for the meshes, but not the mesh object itself.
The embedding of the mesh and what?
The mesh itself, because the mesh itself usually the vertices and the number of faces are not equal. That is what makes mesh processing really hard in deep learning.
You can think in that way. Actually, we have the fixed dimension for how many points. You can think about in a way that is we have fixed number of vertices, but you can think in another way that is we have the dimension that is fixed. And within this dimension, you can think about is a kind of a grading. You can think about that is kind of a grading, and here we have fixed number of the grades here, and if that is occupied, and we have a 1 mark, and that if that is not occupied, that is another mark 0, 1, 0, 1. If that is belongs to the object, that is 1, and if that is not belonging to the object, that is 0. So we have fixed the size from the output. And the output is just marked by somehow whether it belongs to the object or not.
Got it. So it represents an occupancy map instead of a mesh itself. I got it.
Yeah. Well, both can be translated. Actually, that is one-to-one interpolation. You can do that.
True.
Yeah.
Okay. Thank you.
Yeah.
Okay. Thank you. Chandra, do you want to then take this last part of the presentation? And
we would like to thank Guoyu once more. We will use our good old reactions to do this. But thank you, Guoyu. We hope to see you physically here very soon. And we are very happy to see how you're doing. Wish you the very best in the next contest and everything else that you've been doing at RIT.
Yeah, thank you very much. Thank you very much for inviting me to give this talk. I really want to share from our current most recent work to the UD students, and that is really great for me to virtually come back to UD to give this talk.